Okay, here we go.
What?
So, we're going to do this kind of quick. These are all 6. So that makes this 3. That's 6 and 3, which makes this 2. That's 6, which makes that 3. That's 6. Combine those, you get 2. That's 7, and that's it.
Wait, how's it 2? How's it like 6 and 3?
Because it's 1 over 6 plus 1 over 3 equals 1 over r. So this is 1 over 6 plus 2 over 6 equals 1 over r. That's 3 over 6 equals 1 over r. R is 2.
Wait, then why did that one?
Wait, because that has 2, and if each resistor is 6, then wouldn't that be 12?
So is everybody cool with the 3?
Yeah.
Okay, we're done with that. Is everybody cool with this 2?
No.
Oh, because it's 3.
I just did it right there.
How is it 3?
No, but wouldn't
What
it
is
be 12
3?
and 6?
Oh my gosh. Okay, I'm going too fast. Sorry.
Good job, McClure.
All right, so that one's 3.
Yes.
And this is 6 and 12.
Yeah.
Okay, so then that's 1 over 12 plus 2 over 12 should be 4, right?
Yes.
Okay, so that's 4. And then this is 3. And then this is 6. So then that one's going to be 2. And then that makes this total 9 then. Okay, very good. 9. Everybody cool with that?
No.
Okay, which part?
Explain again.
What?
Can you explain again?
Sure. Are you okay with the 3?
Can you just break it down really quick?
Because 1 over 6 plus 1 over 6 is 1 over r. So that's 2 over 6 is 1 over r. So r, right, if I flip it, is 6 over 2, which is 3 ohms. All right, and then, so then over here, this is 1 over 12 plus 1 over 6. So 1 over 12 plus 2 over 12 equals 1 over r. So then r is equal to 12 over 3, which is 4. That's why that's 4. And then down here, the 3 is just like this. And then when we do 3 and 6, that's 1 over 3 plus 1 over 6 equals 1 over r. This becomes 2 over 6 plus 1 over 6 equals 1 over r. So then r becomes 6 over 3, or 2 ohms. So that's why that becomes 2. And then 4, 3, and 2 added together is 9. Question? Did someone say that? I thought I heard somebody say they don't get it. No? We're good? Okay, good. Then we move on. Determine the total individual powers dissipated at each resistor. Okay. So we have to kind of look at current. Did I give you voltage? Oh, okay. This is 18 volts, so this is 2 amps. Are we okay with this? Actually, you know what?
Oh, yeah.
I'm gonna zoom in on this bad boy. Why is it always a bad boy? Why is it not a bad girl?
Because that
Sounds weird.
Yeah, it does sound bad. There's like a weird connotation. Bad boy means tough. Bad girl means like slutty or something. Am I saying something that's not, you know, I'm not saying that you are or anything. Okay. So this is 2 amps coming out of here. These are both 6, so we know this is 1 amp and 1 amp. Yes?
Yes.
And I will do in red, if this is 1 amp and 6 volts, then it's I squared R, right? P is I squared R. So that's going to be 6 watts of power at both of those. And the voltage, because this is 6 ohms, V equals IR. So the voltage, which I'll do in green, is going to be 6 volts.
What the? Can't see the green.
Okay, can't really see the green. How about blue? There you go. Blue works better. Okay, questions? Okay, so we continue on our mad dash. This one has twice the resistance. This right here has twice the resistance. I'll do this so people over there can see what I'm saying. This one's twice the resistance of this. Does that make sense? Okay. So then, what we can do is say that this one is going to have 2 times the current of this. Does that make sense?
Why is it twice the resistance and you have to
Sorry?
Why do you multiply?
Oh, whoops, hang on. Not correct, not correct. I flipped that. Remember, this becomes 3 and this becomes 6. This is going to have 2 times the current of this. There we go. Yeah, because when they're added in parallel, it becomes half. Sorry, 3.5 hours of sleep.
So you are tired.
Well, I mean, I can feel my brain, but like I don't
Did you
feel.
get rid of your Crocs?
No, they're back there. I just need to find where I think actually because of your comment, I didn't like where
Hurt his feelings.
No, I didn't.
No. But whatever, who cares?
Feelings don't matter.
So, exactly. So we have 3i. So basically, this one is going to be 1/3. No, 2/3, right?
What?
2/3 of an amp, and then this will be 4/3 of an amp.
How? What?
Because take a look at this. Do you see that the total current right here at that X spot right there is like whatever? Okay, that's 2 amps. Does that make sense? Right here at this dot.
Yeah.
Where does that go? Into these 2 channels, right?
Oh.
And you see it's I plus 2i, right? I plus 2i. So then that means 2 amps is 3i. So I is equal to 2/3 of an amp.
Oh, okay.
And that's why this is 2/3, and then the bottom is 4/3.
I gotcha.
Okay, now, if the bottom is 4/3, and how much goes on each one? 2/3. Okay, because this is 4/3 right there of an amp, going in, coming out of that this way. But each of these is 2/3. Now, let's see if I can blow your mind with this. This bottom can be redrawn like this. Does that make sense? Do you see it?
Yeah.
It looks all crazy here, but what is all this stuff? What are those lines? What are they? They're just wires, right? They're just metal wires. So is there any difference from this to doing this? See what I mean? Yeah, there's no difference. So all of these 3 are in parallel. So technically, if the 3 of them are in parallel, then I can take the 6 ohms and divide it by 3, so this whole thing becomes like 2. This whole thing becomes like 2 ohms. And we saw that that's what it came out to be, right?
Yeah.
Remember, we did the bottom, which became 3, added to the top, which was 6, that became 2. So that's just a little side thing there to get you to realize that. Okay. How are we doing with the currents on the bottom? Any questions? Now, if you have the currents, do you realize you can get everything else?
Yes.
Right? Because V is IR and P is I squared R. Right? So then do whatever you want. So if I do IR here, I will get the voltage. And 6 times 2/3 is going to be 4 volts, right? Okay? And the same thing is true here. That's going to be 4 volts. That's going to be 4 volts because they're all in parallel. And then they all have the same current, so they're all going to have the same power. So when I go to power, I'm doing I squared R. So I'm taking V times the current again. So I get 8/3 of a watt. And it's the same for all 3. Now, how much current is going back to the battery right here? 2 amps. So, when it goes through here, this is where I have to split it, where I'm saying this one over here is going to be twice as big as that one. Does that make sense? Because there's 1 resistor over here, 2 over there. So once again, I go through that whole gibberish of this, and that gives me this as 2/3 of an amp, and this at 4/3 of an amp. And now I go back through the same stuff again. 2/3 of an amp. I have to remember these are 2 individual resistors. What is true about the current of A versus the current of B?
Same.
Good. Does everybody see they're the same? Because they're in series. And what is true about the voltage of A and B with the voltage of C? Kevin, what'd you say? Oh, okay, good. Yeah, we can use the loop rule, right? And we use the loop rule. I didn't say anything. Then that means this voltage has to equal that one. Okay? So what we do let's figure out this one first. This is 6 times this, so that's going to be 8 volts, yes? And then this is 2/3 times 6. Well, what is that? 4. And this is 4. There you go. Our loop rule is satisfied. So remember, resistors in parallel have the same voltage. Resistors in parallel have the same voltage. Resistors in series have the same, you just told me this, current. Resistors in series have the same current. And now we can go ahead and do our power. This is going to be like 24/3. Wait, 24/3 is 8, isn't it?
Yes.
Oh yeah. So it's going to be 8 watts, and then this is V, and I is 2/3, so that's 8/3. So this is 8/3 of a watt, and this is 8/3 of a watt. So that's the voltage and the power consumed in every resistor in that circuit. All right, now we move on. Oh, we did that. Okay. Okay. If the resistors are all light bulbs, determine the order of brightness. 8 watts, 8/3, 6 watts, 6 watts. Yeah, so the brightest is 8 watts. And then these two 6 watts are next, and then all of these are the same.
Wait, what
How would you like write that on a test?
I would write it like this. I write it with my pencil.
Okay. You're dumb.
You're dumber.
Shut up.
Shut up.
You're dumb. You're not my mom.
I know. Okay. So I would probably redraw this circuit and then just do like 1, 2, 2, 3, 3, 3, 3, 3. I mean, if you look on what you did, what you calculated, this was the 8 watts, this was 6 watts, this was 6 watts, and then all of these were 8/3 of a watt. Or if they were labeled, like if we said this is like A, let me do this in a different color. Let's say this is A, B, C, D, E, F, G, and H. Then I would say something like H is greater than A, which is equal to B, which is greater than F, which is equal to G, which is equal to C, which is equal to D, which is equal to E. Okay or not? That was weird.
Stop it.
And I'm the one who got 3.5 hours of sleep last night.
It's okay, let's just have a napping period. Let's just take a nap.
Yes.
While we were at
Yeah.
state, our entire team turned into peacocks.
What?
Oh my god, I heard.
Is that the noise a peacock makes?
That's the mating call.
I don't want to hear that. That is none of my business. You never want to associate high school students and mating calls. It's just a bad idea.
Peacocks.
All right. Okay, if the resistors became capacitors, what would be the charge on each one? So basically, we got to do the whole thing. Okay, we're going to do basically the whole thing. And then this is saying that it's 6 microfarads per capacitor, right? So then what's going to happen is this is going to become 12 microfarads. This is going to become 18 microfarads. Does that make sense to you?
Yes.
Okay, this will become
Also.
3 microfarads, and that's 6 microfarads. So then if I condense, I get this. I get 12 microfarads here, 18 microfarads here, and I get 9 microfarads there. And now I have to do the ugly thing. 1 over 12 plus 1 over 18 plus 1 over 9 is equal to 1 over C. And then so I do like, 3 over 36 plus 2 over 36 plus 4 over 36 equals 1 over C. So C is equal to 36 over 9 microfarads, or 4 microfarads. What's that?
Oh, never mind.
Questions?
Ah.
Yes.
Yes.
Excellent. You might be able to finish it. Test on Monday. Boom!
No.
Boom!
Wait, is that all it asked?
Oh,
No, I
sucks to
know.
be
It
you.
asked for
Okay,
the.
here we go.
missed the part.
Wait, what happens if you're not
You
here
missed the part on
Monday?
before.
Number 4.
Find like the charge on each one.
Wait,
Oh, the charge. Okay, hang
Clara,
on.
what's the schedule like for like AP? So just go to our class.
The schedule for, what do you mean? You just go to your class? Yeah, after you take your exam, you just go back to class.
Does that mean that I'm basically reading first, second, and third book? Like,
That's a good
days?
Do what?
I'm just missing like my morning classes for like
Yeah.
days.
I'm
Maybe
counting.
missing your class.
Normally when you are not in class because you're at a school thing, I say you're responsible for whatever it is that day. Which means technically if we have a test on Monday and you have an AP test in the morning, you have to come in the morning and take a test.
Wait, what?
But what I do for AP tests is it's like you have an absence.
Oh.
So if you have like 3 AP tests in a row, then I'll say, all right, you can have those 3 days as if you were absent, and then you'll have the 3 days to make it up. You get it? So it's like you're absent from school. I'm okay with
What
it.
if it's like a Monday, Tuesday, Friday?
I don't know, just come back to me. Okay, anyway. So now for this one, so we got to get the charge on here. So when I'm looking like this, when we get this all the way down to 4 microfarads, we have, is it 12 volts? Right, I think it was 12 volts, right?
18.
Oh, 18 volts, okay. So we have 18 volts, and then we know that C is Q over V, so Q is CV. So it's 18 times 4, so we have, what, 52 microcoulombs of charge that have to be distributed onto the things that are connected straight to the battery. So if I can use my highlighter, this one, this one, this one, and that one are the capacitors that get the charge
Wait, why?
because they're connected directly to the battery.
Oh,
Right? Everything else just splits the charge amongst itself. This is why when you have things in series, when you have capacitors in series, it's weird. Because you can have a capacitor that's, well look, we have 12, then on the bottom we have 18, then over here we have 9. So which one determines what the capacitance is? They all do. That's why we have to invert it. Okay, so for this one, if I look at how this is connected, there's a 6 here, a 6 here, a 6 here, and a 6 there.
6. Oh, okay.
Okay. If I look at this is actually what I should look at. And see, this is 12 and 9 connected directly to the battery. So then how is this 52 microcoulombs going to spread itself out? The easiest way to say that is most of it's going to go here. So it's 12 ninths is going to go over here, and then the rest is going to go over here.
How do you know it's 12 ninths?
Oh, wait, sorry. Wait, proportional. How do I do that with proportions? My brain is fun.
Something like 3s.
Well, I guess the easiest. Oh yeah, threes. So okay, good. That becomes 4/3. So then this is 4. Like this is like a 4, and this is like a 3, right? By proportion. So then this one just needs to have a third more than that one, right? So then I'd probably do combine the. I would probably say that this is going to get 4/7 and this is going to get 3/7.
Why 7s?
because I added the two proportionally,
Oh, okay.
right, and then come up with that. And honestly, if I give you this on a test, it'll be easier.
Wait, so it's only going to so if this is like a problem, it's only going to be the ones that are directly connected
Yes, because that's the only ones the battery can give charge to. Okay, so then I take that 52 microcoulombs, put it on, and I'm done. Okay, now the reason this one seems so hard and the other one didn't seem as hard, what is this one missing that the other one had before? It had this. See, it had one directly connected to the battery, which allowed us to use the loop rule and get that charge. And once we know that charge, now we can split up the other charges. Okay, and like I said, the one that you'll see on the test won't be that hard.
What if you don't finish going over test prep in time?
Well, I mean, I'm the one who decides when the test is, so
Maybe we should change.
I can do whatever I want.
He's in it.
I'm the king.
No.
Ouch. Okay. All right. So electric field, that's obvious. Zut, 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 zut. Wow. Wow.
I did that. No, I didn't do that.
Do we need that much?
Yeah, you need to do those onion-y looking things.
Really? I just did like two.
Nope, you need more. Because you have to show that the electric field from this is going into there. Because look what it says.
Oh. I get it.
That's this. All right, next.
Stop.
Wait, little.
If two charges have magnitude of this, what would be the force? So this is whose law? Yeah, F is equal to K Q1 Q2 over R squared. So that's 9 times 10 to the 9th newtons meters squared per coulomb squared. Both of them are 500 microcoulombs, so I can just say 500 times 10 to the minus 6 coulombs squared, because it's an absolute value, right? And then this is R, so that's 1. So this becomes, so this is 9 times 10 to the 9th, and that becomes 20,000, 25,000? No, 250,000, sorry.
That's really big.
Times 10 to the minus 12,
Never mind.
okay? And so then if I get rid of this, that becomes minus 9. If I get rid of that, so it's 2.5 times 10 to the minus 7. And then this knocks out that, so I'll get something, I get 9 times 2.5 times 10 to the 2. And then so that's going to be 1822.5 times 10 times 10 to the 2. So is it 2,250?
I got something really big.
Could be wrong. I may have moved. Yes.
Oh,
Question?
I just want to know that if it's like micro coulombs, do you have to like convert it to
Yes. You have to go to the minus 6. South. R is the distance. But radius, distance, same score. What's that? The reason you call it a radius is because the field effect is spherical. No, you use 1. Yes. Oh, just plug it in your calculator. 9 times 10 to the 9th times 500 times 10 to the minus 6 squared. Yeah, that's the right answer. Basically, I'm just using all the scientific notation. So both of them have 500. It's just one's plus one.
Yeah.
Okay, questions? That is the right answer. It is 2250.
Well, it's just somewhat healthy.
Scientific notation is really cool for helping you do math problems.
I can always get the Malcolm X questions right.
Okay, so here we go. Question number 7. This is awesome. We're going to finish.
No, we're not. Are you excited?
All right, if you were directly in the middle of each charge, what would the electric field strength be? All right, so here's a minus, here's a plus, and here's you. X marks the spot. So the question, what is the electric field strength? How many things, what is the negative going to do here? What does the field look like because of a negative charge?
It's like
Yeah, right, into the charge. So that's from the negative charge. Let me do this. Sorry, let me go with, what's negative? Red or blue?
blue.
Blue?
Yeah.
Okay, red?
No, it's blue. It's
Okay,
negative blue.
so red's going to be positive. The negative is blue. So this is from this. And this is from that.
What? Oh. Okay.
So what I'm doing is I'm actually getting twice. Now, what is true about the magnitude of the charge on each one? It's the same. What is true about the distance?
Same.
The same. So what I can do is just use, say that E is KQ over R squared, yes?
What are,
And I can just multiply this by 2. Okay, so then that gives me 9 times 10 to the 9th times 500 times 10 to the minus 6 over 0.5 squared. And then I multiply that by 2. So 0.5 squared becomes 0.25. And then 500 times 2 becomes 1,000, which becomes to the minus 3, which knocks that to 6. And so I get 36.
what? What? Oh, I get it. Times 10 to the 6. Wait, how's it? Oh, okay. No, I get it.
So just plug it in your calculator. See if you get that answer.
So it's not
I could be
36
wrong.
times 10 to the negative anything?
It's happened 1 or 2,000 times before. So what I'm doing is I'm doing like scientific notation gibberish, right? If this is 500 times 10 to the minus 6, that means this is 5 times 10 to the minus 4. And 5 times 10 to the minus 4 times 2 becomes 1 times 10 to the minus 3. When I multiply 1 times 9, I get 9. When I multiply 10 to the minus 3 times 10 to the 9th, I get 10 to the 6th. And then, oh, it should have been 36 times 10 to the 6th, sorry. And then, because squared becomes 0.25, it's 1/4. So when you divide 9 by 1/4, you get 36. Okay, cool? Yeah.
So if there is another like positive charge on the bottom with a 2 3.
If there was another positive charge on the bottom, yeah, you could do that.
Would that be 3 instead of 2?
Yeah.
And then what if you had one?
What if that top became a plus? What would the field at the middle be?
0.
Ooh, 0. Nice. Nicely done.
And then if you have like a positive, then would those two
Yeah. And then if you added an extra positive on the top, then the 2 positives would cancel, you'd be left with a negative. But if you replace the negative with a positive, then those 2 positives will cancel. All right? Then we move on. Wow. We saw a great movie last night. We have to do physics today. Life does not get better. Okay. If the negative is fixed to the ceiling and the positive is a floating sphere, so we have negative ceiling and this is a ball that's positive, what is the mass of the floating positive? So, something's floating there, what do I gotta do? Force diagram. This is F sub G, this is F sub E, the electric force. Yeah. Okay, hang on, I'm almost done, actually. Sum of the forces equals 0, Fe equals Fg, Fe is K, Q1, Q2 over R squared, that equals mg So I just divide both sides by G, and I solve for my answer. Woo! Done.
Oh.
What just happened?
Wait, so you don't do anything with the negative. So like
Oh, isn't that cool? How much, what was the mass of the thingy?
500 micro something.
Was it milligrams?
No,
Did,
it was,
did I not give you the mass of the ball?
I don't think so.
Okay, well then that's it. If I don't give you the mass of the ball, that's all you gotta do.
Really?
So you do.
Of course, because you can't plug in any numbers.
That's tricky.
Because remember, we already calculated the force, right?
Yes.
So why do it all over again?
Oh, so then you just divide whatever force you got by G.
By G and you're done.
Oh, yeah.
Now, yes.
When it's, I know it's floating, right? It's the same.
Yeah.
Usually it's
It would be hanging from a string. So it's purely being levitated by electric field.
when it's in
I don't know, whatever. I mean, I said floating. And that Sal actually brings up a good point, right? If there's something in a question where you're not sure, and this isn't just for this year, this is for all of college and the rest of high school. When you think a question is unclear, even if it's actually not unclear, ask. Okay? It never hurts to ask. Always ask, even in college. Because what will happen is you'll be taking a class, well, if you're going to one of the UCs or Cal States, you'll be in a room with like 300 people,
Crazy.
all taking the test at the same time. And there'll be all your TAs walking around. Actually, they'll probably be texting and farting around. So you want to make sure that you say, yo, question, and then they'll come over to you and talk to you about the test. Now, they're not going to help you. Actually, you can sometimes get a bleeding heart TA who will actually try to be like, well, you know, if you knew this, you would probably figure it, you know, it means like
Like
they're sentimental, they're compassionate. Huh? No. But, I mean, maybe in liberal arts, I don't know. But even if you have a strict TA, it was a joke about hearts bleeding. Never mind. Anyway.
Yeah.
Anyways, the idea is, I'm trying to say they're more compassionate. They're nicer people. They're not. Yeah, it's that any TA will be glad to clarify the question, right? You just say, I'm not clear on what this question is asking for. These two terms seem like, what Sal said. He said, when you say hanging, that kind of intimates that it's hanging from a structure. Is there a structure? And then I would say, no. The hanging simply means that it's in the air, not touching on the ground. The floating is the other part of it. I would say. Yeah. Question?
What about the other part of number 7, the electric potential?
Oh, sorry. If you know the electric field, then you just, if you know the electric field, multiply by Q, and then you get the electric potential.
Oh, okay.
Because the electric field strength is K, Q, or sorry, not Q, by R. Is this, right? And then electric potential is KQ over R.
Why would you multiply it by another Q?
What's that?
Why would you multiply it by another Q?
You wouldn't. I made a mistake. Well, no, actually, you could do that for energy. Or, yeah, force or something. But yeah, if you just multiply this, or just get rid of one of the R's, and then you're good. Because or you could just do this equation twice. That's fine. You just use that equation. Now, in this one, oh yeah, that's right. Huh, that's funny. If you just use this equation twice. The key is you have to make sure that you remember the charge is plus or minus, because this is actually going to come out to be 0.
What? Really?
You see why? Because like the 1 it's K, and then Q1 is 500 microcoulombs, and then Q2 is negative 500 microcoulombs, and they're both the same radius, so they cancel each other out.
Isn't it absolute value though?
Not for electric potential. Let me see. Watch. I will show you this. Okay, so here, if I take this negative charge, and I show the electric field like this, and then, oh, actually, I should do this. Okay, does that make sense?
Yes.
That's what it looked like, right? And then, if we show, it's numbers. You can see the electric field strength that we're calculating right there. If I take this and put it right in the middle, it becomes 0. See, there's this point, hard to get, but it's 0. And that's because one of the, imagine, it's like the amount of energy that a charge gets here is based upon the electric field strength, and it's based upon what other kinds of charges there are. Right? So because of that, you get an electric potential of 0 there.
So if it's in the center of like two equal but like opposite charges, then it's 0?
Yeah, the key is just make sure that you use this equation. And it's like Q1 R1 plus Q2 over R2 plus ... keep going. So if I give you 5 charges and I ask you to point in the middle, do all of them. So it's just follow that equation. And remember, we derived this equation. All right, all of that should be recorded, theoretically. Okay, now Anne, you had a question about the Avengers.